My name is Sandra Kentish and I'm the Chair of the Victorian Division of ATSI and a Redmond Barry Distinguished Professor at the University of Melbourne. Let me start by acknowledging on behalf of the Parliament Victoria and its members, the traditional owners of the lands on which we are meeting. We pay our respects to them, their culture, their elders, past, present and future, and elders from other communities who may be with us today. Today, we will hear from two eminent speakers about the state of our space industry, the research and developments being undertaken, and the innovative future applications. To fully realise the opportunities to grow the Australian space and spatial industry, we will need a highly skilled workforce and the right industrial policy settings. So it is with great pleasure that I introduce our two speakers today. So I'll introduce them both. Dr. Sarah Pearce is from the Square Kilometre Array organisation. Sarah joined SKAO in July 2021 as Director of the SKA Low Telescope. There she leads a growing team in Australia preparing for construction and operations of the world's largest low-frequency telescope, to be built in Western Australia on Wajarri Yamatji country. Prior to this, for 10 years, she was Deputy Director for CSIRO's Space and Astronomy Program. And let me also introduce Professor Alan Duffy, who's Pro-Vice Chancellor for Flagships Initiatives at Swinburne University of Technology, where he's driving large and ambitious transdisciplinary research through external engagement, including with government, industry and NGOs. This builds on his role as the Director of the Space Technology and Industry Institute at Swinburne. Alan has an extensive background in astrophysics and space research and public communication, with the most recent explaining dark matter particle physics to the public. We're going to lead off with Dr. Pearce giving a short presentation, and she'll be followed by Professor Duffy. We will then have an open Q&A session, but I invite you to post questions throughout the presentations and once we get to the Q&A session through the Q&A function. Please use that function rather than the chat. But I'll now hand over to our panel. So thank you, Sarah.
Thanks very much, Sandra, and thank you very much for having me here today. So I will also start by acknowledging the traditional owners of the lands that we are all dialing in from today. And in particular, I acknowledge the Wajarri Yamatji as the traditional owners and recognised native title holders of Inyarimana Ilgari Bundara, which is CSIRO's Murchison Radio Astronomy Observatory, which is where we will build the SKA Low Telescope. And I pay my respects to their elders past and present, and I'll tell you a bit more about the SKA in a minute. So we are entering a new space race, whether you know it or not. There are 17,000 satellites expected to be launched in the next decade, more than 4 times the number for the decade before, and launch is getting cheaper. It's easier to access space than ever before. We are likely to see both governments and private entities go back to the moon, and private human space flight is already becoming a regular occurrence. But space has its most significant impact here on Earth, in Earth observation, in communications, in life sciences. And because of the size of our land here in Australia and the unique challenges we face as a country, space is perhaps more relevant to us than anywhere else. So I'm going to talk about some of the activities that Australia has planned in the space and the astronomy sector. I'm going to talk about some of the technologies here and a little bit about the skills that we need for this. So the Australian space sector employs more than 10,000 people, and it's worth more than $4 billion a year. And with the establishment of the Space Agency, the aim is to triple the size of that sector by 2030. You may not, though, understand the full breadth of the space sector. It's absolutely not just about exploration and going to the moon. Space touches us all every day. And so I'm going to consider just a few of the areas that are identified by the Australian Space Agency's National Civil Space Priority. So the first of those is position, navigation, and timing. What does that mean? It means satellite navigation, essentially. So you using GPS to work out how to get home, but also enormous range of other users of satellite navigation in industry, including farmers using very precise satellite navigation to allow them to plow their fields. Satellite navigation being used for transport, both in marine and land transport. Earth observations, the next area. Space is absolutely critical in helping us address our greatest environmental challenges. Climate change, understanding our land use, dealing with disasters, predicting the weather. These all fundamentally rely on data from space, data that is large in scale and requires the very latest technology in terms of artificial intelligence and machine learning to allow us to interpret it and model it. And then communications. Satellite communications is absolutely critical to connect us across our vast continent. And Australia is one of the world's premier sites, as well as a ground station for both Australia and other countries to place their downlink capabilities here, so that satellites can downlink their data when they come overhead. Perhaps the most famous use of this is picture here, which I have of Parkes, the Parkes telescope, which was used during the Apollo 11 first moon landing. And the picture I have here is of the 50th anniversary of that event. And that just demonstrates Australia's central role in communications from space internationally. And then there's a whole load of other groups like robotics and automation. We have a very strong resources sector that has unique expertise in robotics, which can be applied to space, which is one of the reasons Australia is working on a moon rover for NASA's Artemis mission. We have expertise that can be applied to agriculture and medical science, for example, for space. In agriculture, imagine the possibilities of very low water plant growth. Imagine that in space, but then perhaps more importantly, imagine applying what we have learned in space in that very harsh environment back on Earth, and think about how that can help us live here in the environment and in the climate that we do. So if we go on to the next slide, I'd like to talk about one particular example of space influencing what we do here on Earth. And this is the Aquawatch mission, which was recently proposed by CSIRO, Australia's National Science Agency, and the SmartSat CRC, which is a collaborative research centre between academia and industry in the space sector. The health and quality of our waterways, both inland and coastal, is under threat from increasing human activity and under pressure from the effects of climate change, so increased drought, more sediment from bushfires, more storm events, toxic algal blooms. We have water quality sensors across Australia, but they're restricted to the specific area where they're installed, and there are fewer of them than you might imagine. So the proposal for this system is for a merging of satellite data and sensors in rivers and streams with data analysis and artificial intelligence, which will make an integrated system that will deliver accurate monitoring and forecasting of water quality across Australia and even the world. So once in place, you'll be able to get real-time updates and predictive forecasts of the water quality where you are. So if you go to swim in a water hole, you'll be able to look up on your phone, what's the quality like here? There are 6 pilot sites already in Australia and 5 internationally for this project, and CSIRO and the CRC have invested $83 million initially to design and develop the first stages of the system. In this first step towards what will be a world-leading program, and is already attracting interest from other countries who have water quality questions, like Canada and in Europe and California. So that's one great example of space for direct benefit of Australia. Now I'd like to talk a little bit about the Square Kilometre Array, where we use cutting-edge R&D technologies to contribute to astronomy, a slightly different sector. So we move on to the next slide. So this is a picture of the Square Kilometre Array Low Radio Telescope, which is not built yet. This is an artist's impression. But SKA Low will be the world's largest radio telescope of its kind. It is being built up by an international collaboration of 16 member countries. And they're building 2 telescopes, one in Australia, in Western Australia, and one in South Africa. In Western Australia, in the Murchison region, about 350 kilometres inland from the coast, we will build 131,000 Christmas tree kind of antennas that you can see here. And each of these antennas is in fact about 2 meters tall. And by building these and spreading them across 75 kilometers of the outback, we will build the world's best radio telescope for being able to look back towards the period not long after the Big Bang, when the first stars and galaxies started to shine. We call that period the cosmic dawn. And if we can see this, it will be the first time that we've been able to detect and map this in human history. And it will help us to explain how stars and galaxies evolved, how the universe itself evolved after the Big Bang. There's a lot of other science goals, but what I want to talk about a little bit about is the technology that will be required for this. Because while it's a great logistical effort to deploy this telescope in Western Australia, and we start building it this year, and it will take us 5 years to build it, the real challenge will come with dealing with the enormous data rates that come out of the telescope. So the telescope will produce terabits of data a second. That's hundreds of millions of Netflix movies over the course of a week, downloading 24/7 and needing to be processed by us in a supercomputer in Perth. So the big data challenge is where we really sit at the cutting edge of technology in radio astronomy, and where we develop skills and capability and innovation, which we can apply across the whole field. There are 2 really good examples already from the preparatory work that's gone to the Square Kilometre Array so far. First of all, from Swinburne University, where Alan's from, Fourier Space, which is a spin-off company which develops ultra-high accuracy systems for timing very fast-spinning stars called pulsars and for looking for them. This is really high-speed, world-class, cutting-edge digital signal processing. And then secondly, quasar satellite technologies, which are using innovative radio cameras developed by CSIRO for astronomy and applying them to satellite communications so that they can talk to more than one satellite at a time. And there's already $6 million of venture capital funding gone into that spin-off company. Another key area that we're looking at is how we track the rapidly increasing number of spacecraft in the space environment. This is called space domain awareness. Of course, collisions of even quite small objects in space can be devastating for other satellites and for our ability to use low Earth orbit. So, for example, the Murchison Wide Field Array, which is a radio telescope, another radio telescope in Western Australia, led by Curtin University, has been testing how they can use their radio astronomy technology to track objects in space, and are now partnering with Nova Systems. They've built an array in South Australia that uses the FM broadcasts that you get from radio stations, and they bounce off objects in Earth orbit. And the telescope that they've built is so sensitive that it can easily see those reflections and use them to track objects in space. Now, I mentioned that SKA is an international partnership. It has 16 member countries and is a treaty-based organization. And I just want to flag for you this great example of Australia's contribution to the international community. We have a long history in radio astronomy. It's one of the first areas, we were one of the first countries in the world to do radio astronomy observing. So we have great expertise here, but we also have a landmass, which is particularly well suited to this, because you need, in order to observe very faint radio signals from space, you need a quiet landmass. So what you need is somewhere with empty space with not many people. And then we have a really well-educated workforce as well. And so this is the first time that Australia has hosted one of these mega science international projects. It's a €2 billion project. And the first time that we've hosted this kind of intergovernmental organization as well, building a large scale project and bringing a highly educated and committed workforce to Australia. Just for the next slide for 1 minute, an important aspect of our work here is our partnership with the Wajarri Yamatji, who are, as I mentioned when I started, the traditional owners of the radio telescope site and the native title holders. This is a critical partnership for us. There's an Indigenous land use agreement, which allows us to build the telescope on their site. And we were very grateful earlier, later towards the end of last year, when they gifted the name for the site, which is called Inyarimana Ilgari Bundara in Wajarri language, and that means sharing sky and stars. So we really hope that our collaboration here with the native title holders will be a world-class example of how a cutting-edge technological development can take place on the lands of the world's oldest living culture, and in partnership and in joint respect with them. So then just finally, we go back to the slide that I started with. And in this case, not to look at the parks dish at the back, but to look at the kids in the front. Because what we absolutely need in order to deliver all of this, the space, the astronomy, the high tech, is a really highly educated workforce with a range of skills, technical skills, engineering and software, but we also need people in finance, in communications, in HR, and we need a diverse workforce. So we're working very hard to build a gender balanced workforce that makes the best use of all the capability in our community. So we're bringing in expertise from overseas and from across Australia, but we know it's also important to grow our own skills. And so we're looking at apprenticeships, and in particular, because we've got a lot of our staff are based out of Geraldton, we're interested in how to grow skills in regional areas and in the opportunities for kids from regional areas to learn science and technology and then apply that where they live. So with that, I'll hand back to Sandra for the next talk.
Thanks, Sarah, for an excellent presentation, but I'm going to hand straight to Alan for him to also present.
Okay, thank you very much all. So I'll try to give a bit of an overview on the more of that space industry aspect and the uses of space, and then particularly, of course, the opportunities for Victoria. Before I begin, so excuse me 2 seconds. Before I begin, I'd like to acknowledge the traditional custodians of the land for which I'm joining, the Wurundjeri people of the Kulin Nation. I want to pay my respects to elders past, present, and emerging. Extend those respects to all Aboriginal and Torres Strait Islander peoples. Very broadly, when we talk about the space industry sector, and there's not really an astronaut in this picture of me sitting maybe on the space station, but this is an enormous global industrial effort. It is a revenue generation of $350 billion annually. That's US, as estimated by Morgan Stanley, and is expected to grow to 1 trillion annual revenue by 2040. And it spans the gamut from the upstream, which is the hardware, the rockets that launch the satellites, the examples of high-end technology, sensor developments, beautiful collaborations across astronomy, for example, as we heard from Sarah in terms of spin-outs from our radio astronomy, but also too in the optical astronomy. So that is the visible light that we are seeing with all of these kinds of sensors are taken and used for very much down-to-earth use cases. So essentially, you end up turning the camera from the stars back down to Earth. And as we go progressively towards the downstream, towards the right of the image, we have the receivers. So that's the ground communications capability that Sarah mentioned, the ability to receive and uplink to those orbiting satellites, essentially extending now the internet to low Earth orbit, essentially, and in particular with the examples of, say, SpaceX's Starlink, There are thousands of these communicating satellites providing global coverage. It's really an extraordinary transition that has occurred in just the last couple of years, where there's now almost nowhere on Earth that you can't get a signal, except for my kitchen, as it turns out, at my house, which is still a dead spot even today. The further down towards the downstream then is, what do you do when you receive that data from space? So that is the imagery that you're capturing from orbiting satellites. There's a range of capabilities up there, but it is very much targeted on the end users, and it can have a seamless connection between the images from space, for example, and drones operating almost autonomously on ground, so providing a ground truth data set. And that's the brilliance of the Aquatch program that the CSR is leading, Sarah mentioned, where it's seamlessly integrating both satellite capability and the so-called ground truthing, the ground measurement points, to gain a better overall view of our nation. At Swinburne, we have several focus areas. I'm going to give a very brief overview about the works that the team are doing. I won't speak too much about the extraterrestrial resource processing, but very simply, it's mining the moon. There are a number of collaborations underway, including with the Tier 1 miners here in Australia, but also with NASA and others, to explore ways to liberate the resources of the moon and do so in a way that is both responsible and sustainable, because it is a common heritage to us all, but there are opportunities to resupply our astronauts. The water from the moon can also be broken up into hydrogen oxygen as literal rocket fuel. So we can resupply astronauts, we can also refuel rockets for the further missions to Mars, and even refuel satellites in orbit. It's all very exciting stuff, but it is a very small market at this stage. So I'm going to focus on the other uses. Material and coatings for space. Space is an incredibly hazardous, extreme environment. It demands the best of our material scientists in terms of that skill set. It's foundational knowledge. It is very much applied, selecting new kinds of materials that are lighter, that are more weather resistant or more resistant, can handle extremes of temperature, pressure, and the like. So what we are designing for space has incredible applicability down here on Earth. And in fact, one of the biggest connection points of the last year alone has been the translation of a lot of the high-end materials that we were developing for space that is now finding its way into the hypersonics domain. So that is the fast missile segment, the push that Australia is making. And it is in part thanks to colleagues like Andrew and Chris Byrne at Swinburne that we have a capability of Victoria that can be readily used for the national good. We also have a high-end capability in developing electronics that can survive the hazardous conditions of space. There's a lot of radiation up there that can fry your satellites. There is an enormous worldwide effort to build hardier electronics. Again, this is essentially electrical engineering background, but now at an incredible level of capability, taking the best and brightest out of CERN, for example, and trying to find ways to connect that into both satellite operators, and there's a very much a strong defense focus there again, but also on ground, where you can make drones and other aircraft more resilient to both to hacking, but also into accidental radiation impact. So a very critical bit of work that has both the space, but also very much down to Earth opportunities. We see a unique environment in space, the so-called microgravity or zero-G environment. And when we remove gravity from the equation of growing things, it changes. It changes the result. And we can see, gain lots of insights into life sciences through the experimentation in that microgravity environment. Victoria is an absolute powerhouse. There's a Victorian-wide network of microgravity experimentation. Rebecca Allen leads it at Swinburne. Somewhat perhaps differently here at Swinburne, though, we retain the largest and still actually sadly only schools program to the space station. So we have students who design and build experiments that then fly to the space station. And the bottom right is one of the little micro capsules that they build, fly in the space station and come back. And essentially every student we've had through that program has then gone on to have both STEM degrees, but then through that learning experience have obviously found their way into the space sector as well through work experience with the space station age 17. That's pretty hard to beat in terms of competitive placements for the ultimate goal of a career in space. The very much largest opportunity, however, is in that downstream area. So this is where we take the data from space. The program at Swinburne is called Remote Sensing, or AI for Space. And it's the marriage of the very latest computer science graduates and the very latest discoveries in AI, together with these terabytes of data that pour down from orbit every single day, that both in pictures on the left, that we can begin to classify different kinds of objects autonomously, automatically, take censuses of buildings and map for changes. There are slightly different techniques in the middle that allow you to explore the land types, cover if it's urban. You can also do the same for ice monitoring at the poles. And then on the right, you can do change detection in particular for flooding. And that's an example I'd like to close on. But very much for an agricultural perspective, space has become an enormously important source of monitoring information about crop health. This particular instance, we're actually seeing individual vines being monitored, and the different colors indicate different varietals. I can assure you they all look exactly the same to me. They just look like green vines, but from space. And with this kind of sophisticated AI behind, you can actually begin to tell the difference of the varietals and their health and other beneficial insights. The same is being done by Data Farming, a Queensland company for agriculture more generally, particularly wheat and grains. We can also use it to map, again, entirely autonomously. You set this process up, but we can map vegetation growth. This was a project with EY where we supported a mining company's railway management team. So from space, we could see the entire network, and we could tell them when there was an encroachment that they would need to start to plan to burn back. It allowed them to be more selective in the burns that they did, because there is a bushfire risk if it gets too close to the tracks and passing trains cause sparks, which can ignite. So if you can be more proactive and selective, you can do this increased safety management process at reduced costs, because it's all now coming from automated process using satellite imagery, as opposed to sending people down the railway lines to map by eye. But of course, you're also doing it with fewer emissions, since you're able to be more selective in your burns. Very much bushfire detection is one of the key areas that we see as space fulfilling. This is some beautiful early work by Jack White, who's now gone into EY, but also Alex Cordenrow, who's I hope perhaps in the audience, or certainly within GovHe's, He's did some fantastic work around using astronomy techniques. And I won't go into the details, you can ask me in the chat if you like, but essentially astronomy techniques to see the difference when a fire essentially ignites. So this is really nice preliminary work that won an international competition, in fact, between Australia and New Zealand. And then finally, that leads me to disaster response. So it's not just about detection of bushfires, it's the monitoring, it's the ability to use different wavelengths of light to see through the smoke and see the fire on the ground, measure its intensity, and of course, feed that back to the first responders, to the firefighters on the ground. And it's closing that loop that I think is the greatest hurdle that we now face. We're technically able to now do a lot of this work, but can we get the right information into the right hands to guide their decision-making at the right time? Now that, I think, is the frontier. We also have examples of in flood response. And this is an image from floods in New South Wales. Now, sadly, we had these similar floods in Victoria just before Christmas. Incredibly, and as far as I can tell, a national first, satellite data was used to monitor the flood in real time, to load that flood front and indeed do modeling, predictive modeling, to see where would the floods then go, and inform people on the ground, again, in real time, to inform their sandbagging, for example. So an incredible use of satellite data, making a real world impact. And Victoria was, as far as I can tell, the first state and territory in the country to do that. And again, the solution there was both a technical, some very technical work done in flood maps and the like, but it was also in terms of solving procurement processes, ensuring that there was, in advance of the disaster, a procurement list for the satellite imagery and how it would be sourced and secured. So again, that sense of forward planning and a holistic approach really can make the difference on the ground. And I'll stop there.
Thank you, Alan, for going for a very interesting presentation. We now have some time for a bit of discussion, and I would encourage the participants to post any questions into the Q&A section because we don't seem to have any there yet. But let me start by asking a question of both of you, and I know Sarah touched on it briefly. We're coming into space technology as a country fairly late. There's many countries been playing in this space for a long time. So what do you see as our competitive advantage versus some of these other countries? Sarah, do you want to go first?
Yeah, I'm happy to, Sandra. Well, I mean, as I touched on, we obviously have a geographical advantage here, right, as a large landmass in the Southern Hemisphere, but that's not enough. What we also have is a technological and a skills advantage. So we have, you know, a brilliant set of innovative startup companies in the space sector in Australia, who, when I was in CSIRO, I did some work with, and it's really exciting to see the ideas that they're coming up with and how they're applying them to everyday life using space technologies. And the other thing we have is a really great set of universities, and so a highly educated science and technology populace. And so we've been welcomed, I would say, with open arms by the international community, who are extremely keen to partner with Australia and to engage with us in the areas in which we do have expertise, and to bring us into the international space community.
Mm-hmm. Do you want to add anything, Alan, to that?
Yeah, coming in late, we don't have to support legacy systems. So if you think about the telecommunication example, in the era of optical fiber and mobiles, why would you, not having an existing copper line to also support as you try to upgrade, for example, like a lot of Africa, can be played as an advantage if you have the right government and industrial collaboration to make that leapfrog. And that's essentially what we've been able to do. We have new companies like Quasar, as was mentioned, but there's another one, Fleet, which does from ground to satellite direct communications. With nothing out there, they had to build from scratch, and they built it with the very latest technology, very latest capabilities. And that space company was just awarded the most innovative mining company award at OSMINE 2 weeks ago, because that link up to comms allowed them to place sensors across an existing mine site in a way essentially infrastructure free, and unlock an entire new way of scanning for critical mineral resources. And again, it was entirely because they started from scratch.
Thanks, Alan. And Alan, you've touched quite a bit on how R&D in this space can benefit Victoria directly in some of these enhancements. Are there broader reasons for us to invest in research and development in this space?
There's a very significant and direct payback in terms of that investment, where you get new capabilities to lift productivity in the ag tech sector in particular, but of course also disaster relief. I think there's also a point around unless you are, as a state or nation, a designer of these kinds, or a developer of these kinds of technologies, you don't actually really understand them. You certainly can't push them to their limits. In fact, there was an example that Sarah was alluding to around the use of a telescope in Australia that was then able to use reflected triple J, I think it might even have been the station, triple J signal bouncing back off the junk that's going around for our heads for tracking. Now that's that's wild. Like, that is a very impressive capability. And it was only because we had built the telescope and understood the telescope that we could trust the telescope and push it to its boundaries. So I think whenever you're pursuing new R&D capabilities, you can't reap the greatest benefits from it unless you have been instrumentally involved in its development. Now, those are exactly the high-end, high-value jobs that we want to do. It's very hard to outsource that kind of work to lower cost, lower wage nations. So I think it's exactly the kind of thing that we want to be pursuing, not just because, of course, we repeat multiple benefits to our end users as well.
Mm-hmm. And Sarah, you touched very much on the need for a skilled workforce. What are the types of skills we'll need? What is the workforce we need to be training? Where are the gaps?
Yeah, so we actually need skills all throughout the science, technology, engineering, and maths kind of capability. So, I mean, my team, for example, that we're growing, and we'll have 150 people here working on SKA, will have capabilities all the way through from kind of tradies and technicians, all the way through to PhD qualified engineers and scientists. And so we need that whole range. One area that we are particularly challenged by at the moment is in the software and computing space. There's an enormous demand for people with skills in this area. We're not producing enough people with skills in this area, and it's a very fast moving area as well. So we need to be keeping up. AI and machine learning are consistently now coming through everything that we do. Certainly all our data will be analyzed in that kind of paradigm. And so those are also skills that we really need to look for. So really it's the whole set of STEM skills, I would say, Sandra, that we need. And we need to look at both how we import those skills, but also, and probably more importantly, how we grow them domestically.
Mm-hmm. And Alan, I know you've touched on this and when we've talked previously. Can you utilize those skills once we've developed them in other fields? Do they play more broadly?
Yes, absolutely. And I think it is actually in particular the VET skill set, so the so-called space tradies, I think, as our head of the Australian Space Agency put it, Enrico Palermo. But I think those kinds of skills and certs that are being offered to our students, for example, at Swinburne or dual sector, they can have wide applicability. We see in welding the demands for space and the building of rockets, and we have a partnership up with Gilmore, which is literally a rocket builder in Queensland as part of their supply chain. The level of welding skills that we train our students to meet their needs then is more than enough for every other kind of welding standard one would need, except, interestingly, for subs. That's just a little bit harder. It's a higher pressure environment, essentially. So it's actually harder to build subs in space. But the key for us is everything we are doing in terms of the training, and this is now sector-wide, is about a general skill set, a general demonstrated capability with industry placement. And that's, I think, the key aspect. The space sector is growing quickly. It is taking on a number of interns, essentially, to train up in their very specific ways of working. It's been far more accepting, I think, of new grads coming in that way because of this insatiable demand for talent. So it's been a very positive and productive relationship between the university sector and the industrial base, where we're seeing essentially all of the students that we can provide are getting taken up, are getting that additional specific training. We've given them the foundational skills that they can then apply to any other field, but very specifically as needed for space. The companies are taking them on board in work integrated learning and internships, and that's something I would love to see other sectors do. It's something the space sector is having to do, essentially, because of the talent shortages we're seeing across that pipeline.
Now we are running out of time, so I'm just going to close with the one question we have come through on the Q&A. So to read it out, if we take advantage of being a newer player, how do we avoid getting stayed or stuck in old ways once we're involved? So perhaps if you both comment on that and any other concluding remarks you wish to make.
Well, do you want? I
mean, you go.
Look, I think one of the great things about developing our own space capability is that we can use it to solve our unique problems in Australia. And I mean, Aquawatch was an example of that, but there are lots of others. And space is difficult, right? The space environment and the questions that you get asked and what the skills and technologies you need to develop in order to be able to do things in space do make you be agile. You know, they make you push the boundaries of things. And so I think it's really core for us to be asking those really difficult questions, have a really strong vision of what we want to achieve and how we use space to address challenges in Australia. And that will help keep us at the cutting edge.
Thanks, Sarah and Alan.
Yes, well, it's a global market. So we are exporting. Australia is a small, relatively small market size. We are exporting to that international market, and that demands excellence of us. And we will continue to innovate because we have to stay competitive. So we can thank the global market for that.
Thank you. Thank you, Alan. Thank you, Sarah. We have run out of time, but it's been a really interesting presentation. If you would like to follow up with Sarah or Alan after this, I'm sure we can put you in touch with either of them. So otherwise, thank you for your time, and we'll finish there.